Hello everybody and welcome back to our parallel programming and computer architecture class. Um, in this unit, I will be talking about the basic foundations of parallel processing and parallel architecture. We start with a short history of supercomputing, then I'll walk you through some basic foundations about how computing platforms started out. We talk about several options and architectures that have been traditionally in place, and then we'll take a look at newer paradigms and newer architecture technology that came out, and we'll get an overview of NVIDIA and CUDA. And then we move into some hardware overview of the platforms that we have, and then we get the class going, rather on the hardware side of it course, and get some basic understanding of hardware technologies that are essentially used in the general purpose computing platforms such as central processing units or CPUs. The majority of this class, though, is going to be devoted and dedicated to the parallel programming and acceleration techniques and parallel patterns that can be utilized to accelerate serial processing that can be done traditionally on CPUs, and how we can go about and get this to the next level by utilizing the graphic processing units or GPUs. But before we do that, I would like to start talking about supercomputers. Supercomputers essentially are high-performance computing platforms that can be used to essentially run a massive amount of processing and to be able to do it efficiently. There's a website called Top 500, and on this website you can see the list of the fastest supercomputers in the world. So let's click and take a look at it. So what I would like you to do is, which will be one of our assignments, is to go on the Top 500 website and take a look at the fastest supercomputers there. Look at what is going on in the supercomputing and high-performance computing area and arena, and then according to this website, you can list and see the list of the fastest supercomputers that are coming about, and then you will be able to analyze them side by side and see how they are essentially developed, and what technologies is essentially at the core and the soul of them. Back in 2010, in the supercomputing conference in Germany, NVIDIA GPU-based machines were basically listed as the second most powerful computers in the world. Basically, the supercomputer that utilized NVIDIA GPUs or graphic processing units made it to the top 200. And as you can see in this list, the second fastest supercomputer in the world, Titan, basically utilizes the NVIDIA K20 architecture. One of the reasons to look at supercomputing, and essentially to try to see why supercomputers are going to be at least a dominating factor in the high performance computing, rather also in the ubiquitous computing, basically your simple desktops and your simple basic computing machines, personal computers and so forth, is the fact that by combining or putting together your CPU and GPU, your central processing unit, and your graphics processing units together, what you can actually accomplish is what is the goal of supercomputers and high-performance computing. And that is, you utilize your central processing unit for the purpose of taking care of the core processing or generalized processing that is needed based on your application. For example, maintaining memory, maintaining synchronicity, and maintaining your generalized processing that CPUs are good at, and then relegating, or rather delegating, your specialized processes into your GPU or your graphics processing unit. Because of the fact that graphics processing units are very highly specialized units, specialized computing architecture, and they have very specialized computing architecture that can make use of and take care of specialized processes, such as fast memory management and certain kinds of parallel patterns that these processing units are designed to work best at. By combining these two, you will be able to essentially accelerate any kind of application you have. If you take care of two basic things, take care of understanding and separating the powers and the processing that needs to be done on CPU and on the GPU. And secondly, taking care of implementing your algorithm and make it into an algorithm that makes use of data structures and computing patterns that are efficient and specialized for parallelized processing. By doing this too, you can essentially create a supercomputer in your desktop. And we will try to accomplish some of these, and we will be able to see that easily you can, with the purchase of a relatively recent CPU and a very good graphics card, not necessarily the most advanced, but a reasonable graphics card, NVIDIA graphics card, you will be able to essentially create a supercomputer with several teraflops of performance at your desktop. Before I go further into the class, I would like to mention a couple of projects that make use of graphics processing units, or GPUs, for the purpose of their purpose of high performance computing. Bionic and folding at home. I would let you research Bionic as your first homework assignment that we will see in the class, and but I'll talk about folding at home. Folding at home is a project that is run at Stanford University, and their plan and their goal is to come up with patterns of protein foldings that are useful for studying certain kinds of diseases and certain kinds of genetic reactions between the host or the human body and certain chemicals. The problem with this folding of proteins is that they are massive. There is a massive amount of data that needs to be done to be able to go through a basic simple folding of proteins that essentially, as a result of doing so, you will be able to understand how human bodies and human genome interacts with either certain anomalies such as cancer and non-communicable diseases, and also with some certain medical and chemical compounds that can be used for targeting a certain anomaly or a certain kind of disease. The problem is, as I said, there's a massive amount of data that needs to be taken care of to be able to go through a very simple folding process. However, this process, as massive as it is, requires very basic, simple, repetitive processes. Now, if you take one computer and try to do it, you will need in the excess of tens of thousands of years of processing power to be able to do one simple folding. But if you combine a bunch of computers together, because of the simplicity in the underlying pattern of the folding problem that you have here, you will be able to parallelize it and let each computer take care of a basic pattern, a basic part of this process. By combining this, you can accelerate your process, and then you will be able to basically do it in several hours for one protein. Now, again, because of the simplicity and the specific properties of this problem, you can even further accelerate this process, not only by having a bunch of processing units to do the folding all together, but also to use specialized processing units, such as graphics processing units, that are good at certain kinds of processes, namely geometric calculation. Then you will be able to even further specialize and accelerate your process, because a three-dimensional folding of a protein in three-dimensional space is basically like what graphics processing units are good at, three-dimensional calculations of three-dimensional objects. And they are highly specialized for doing these processes very, very efficiently. So by now not only using a bunch of GPUs to run the process, but also to using their specialized processing power to calculate this three-dimensional geometry, we will be able to actually accomplish a lot. So folding at home, this project is designed to utilize this process to basically create a parallelizable high-performance computing based on graphics processing units that are essentially at the core of any kind of personal computer, almost any kind of gaming console, such as Xbox and PS3 and PS4. And then the users will be able to enroll their processing platform, such as their Xbox or PlayStations, and then while on the computer is on the internet and the player is not using it or playing a game, the idling of that computer can be tapped into by the Folding at Home project, and they will send the calculations to your computer, either your PC or your game console, when it's idling, and your game console will basically take care of some unfoldings of some parts of the genetic material and the proteins that they have to be able to perform the task that that Folding at Home team needs to do. So this being said, I would encourage you to go on both Bionic and Folding at Home websites and study those. And as I said, the Bionic will be a part of your first introductory assignment here. Now that being said, you can see that, and of course from the top 500 website, look at certain supercomputers out there that are essentially utilizing CPU/GPU combination to create a massive amount of processing. And Titan, that I just mentioned earlier, it basically its series will come up with over hundreds of thousands of CPU cores and tens of thousands of GPU boards, with the goal of processing in the excess of 20 petaflops. That's petaflops stands for floating operations per second, which is a massive amount of processing units. That's 10 to the 15 floating point operations per second. And that is what the goal of supercomputing and high-performance computing is. Almost all of the processor work is based on a process that was developed by von Neumann, who is considered one of the fathers of computing. In von Neumann's approach, the processor would require to perform 4 tasks to be able to perform an instruction or a unit of processing. Basically, the first process that needs to be done is to fetch the instruction from the memory. That's the current instruction that is going to be processed. Then a controller would take care of decoding of that instruction and creating the architecture and the circuitry needed and required for carrying out the instruction. Then the execution of the instruction will take place in the central processing unit. And once this instruction is performed and executed, then the result of that instruction, if needed, it is going to be stored. And if you think of the storage as the storage into memory, then you will be able to utilize the system bus to be able to store the data back into the main memory, or you can consider that as a storage into the onboard registers that are close to the central processing unit, which is a part of the central processing unit in this architecture. So the process starts from the main memory. It fetches the instruction and the data that are needed as a part of operation and the operand, fetches those instructions and the parts of its operands into the registers. Then control unit would take care of the decoding of the instruction, creating the processes that are needed for the ALU, arithmetic logic unit, to execute the process and then store back the results in the memory. Usually if you look at a typical processor nowadays, they run at a 4 gigahertz speed. That's 4 million operations per second. And if you look at a DDR3 memory, which is our general memory out in the market, and an i10 Intel device, you can run at anything up to about 2 gigahertz of operation. But inside of the i7 architecture, an Intel i7 core, you look at least 4 processors or 4 cores in one device. And so if you use hyperthreading, you'll be able to actually double the speed of your processing by an Intel i7 device. Now, one of the problems with the Van Neumann architecture is that when you have a program, each of the instructions in that program need to go through that 4-stage process of being fetched, decoded, executed, and stored. When you have a lot of data and a lot of instructions, which is typical of any kind of program, that need to be executed, this 4-stage process needs to happen. And what amounts to the biggest problem here is the bottleneck, which is essentially how fast the data can be fetched into the memory and can be stored back into the memory after the execution of your instruction. So notice that 2 of those 4 operations we talked about earlier, the fetch and the store, the first cycle and the last cycle, require memory access in the form of reading and writing. So it doesn't matter how fast your processor can execute the data and the instructions, or how much memory you have. What really is the issue here at hand is how fast your instructions and the data associated with them can be fetched from the memory, and then once inside the CPU, the decoding and the execution may not take much, but then how fast you can write them back into the memory. Now, if you have a process that is repetitive, so if you have an instruction that needs to perform an operation, such as adding 2 numbers, over a repetitive amount of time, like 100 times, 1,000 times, 100, or 100,000 times, then this process essentially would require all that operation to be fetched every time the instruction is to be performed from the memory. Calculation happen in the CPU and then store back into the memory. This is basically very inefficient, as you can see, because of the fact that the DRAM, or the dynamic RAM that we have, although they're huge in size, their bandwidth, their access time, rather the amount of time it takes to read or write a byte from or into the memory, is orders of magnitudes slower than the speed at which your CPU cores can process and can handle the execution of the operation. So this is what becomes the bottleneck here. To alleviate this problem, an alternative memory has been created. And so the CPU manufacturers, Intel, AMD, and others, basically incorporate a smaller layer of memory closer to the CPU cores. and closer to the register banks of the CPU, which essentially will um, create a tiered layer or an hierarchical mechanism for memory access, so that when an instruction is being fetched for the first time, it's going to come from the DRAM, and then it's going to travel through several layers of cache, and I'll talk about these layers of cache in a little bit, and then they will be hosted close to the to the um, to the cores of the processors. So the higher you go into the hierarchy, the faster the access, read and write access to your cache memory will be, and also their sizes will be smaller. So let's take a look at them in a backwards fashion. Let's suppose that we have a two-core processor, so our CPU, our chip, is basically split into two subsections, two neighborhoods. And each of those will have their own dedicated core, which basically will be a central processing unit of its own. Each of those central processing units will have their own register banks and their own control architecture and arithmetic logic units. Each of those core processors would have access to their first layer of cache, or primary cache, or layer 1, L1 cache, which is basically split into two sub-cache systems, an L1 instruction cache and an L1 data cache. These are very, very high-speed memory units that are hosted very close to the register banks of the CPU core, which makes them hugely expensive, so they would be very limited in size. So the first level of cache are typically near the processor clock speed, and they can be very, very small, essentially 16 kilobytes to 32 kilobytes in size. But they are hosted on the same hardware architecture and circuit as your CPU is, so therefore the access to these cache systems are going to be faster. To speed up your process and to compensate for the small size of level 1 cache, each core will also have their own copy of level 2 cache. So the level 2 cache are usually bigger, about 256 kilobytes, and they're generally they are basically slower than level 1 cache. And then finally, all of your cores, in this case the two cores that I have here, they're going to have access to a level 3 cache, which is going to be hosted off chip of my CPU, and then that cache is going to be much larger. So for example, in the case of Intel i7-920 processor, it's about 8 megabytes of size, and they're going to be much slower than level 2 and level 1 cache instructions as a consequence, or cache units as a consequence. And finally, this cache will be connected to the DRAM, dynamic RAM, which is going to be on your motherboard, so that's going to be completely off chip. Now, this architecture is very interesting. It has its limitations, but it's really, really useful in speeding up your process a lot. So how does this work? If you were to look at a very simple program that just basically had a simple essentially instruction, and you were to fetch one instruction and run it, your instruction would be fetched from your memory into level 3 cache, and then into level 1 cache, and then into level 1 instruction and the data cache, and then they're going to go into your core processor, and then they would be getting processed. The problem with just a simple single process is that, or single instruction, is that you're not going to utilize your cache system here at all. What cache would be essentially very, very highly useful is when you have a lot of repetitive processes that require certain kind of coherent patterns of data access and instruction access within your program that make use of the cache system and speed up your process. So if you were to run a billion completely independent instructions from each other with absolutely no relation with each other, each of those instructions would have to be independently fetched from the memory into your level 3, level 2, level 1 instruction and data cache, and then each of them will go into your your processor and get executed. Notice that this, every time you have an access and a fetch from the memory, you're going to basically need to go and run at the slowest speed, which is the speed of your DRAM down here. What cache helps with speeding up the process is that whenever you need to revisit an instruction that has been encountered before, or data that has been encountered before, and it has been already fetched from the memory, you won't have to go all the way down to your main memory to fetch it. So if the instruction or the data already exists in the level 1 cache, or level 1 instruction or data cache, your processor would access them very, very efficiently between level 1 data and level 1 instruction and the register bank of your core. If they don't exist in the level 1 cache, then your instructions are going to be looked up from the level 2 cache. And if they do exist there, then they're going to go up, populate the level 1 cache, and as a consequence go back and fetched up into the memory of your register banks of your CPU. If the instruction does not exist in level 2 cache, then you're going to have to go and access it from level 3 and go finally and access it if it's not in level 3 cache, and get it from your DRAM. So notice the first time you access an instruction or a data, you'd have to go down to the DRAM, fetch it up, and process it. But then it's going to be, a copy of it is going to be in level 3 cache, a copy of it is going to be in level 2 cache, and a copy of it is going to be in level 1 data and level 1 instruction cache systems for your CPU to access them the next time it needs to access them. So this is really good news. I mean, if you needed to revisit some instruction or revisit some data that you have been processing, you don't have to, if they are in one of those cache systems, you don't have to go all the way down to the memory and slow down your process. So your CPU processor cores can access those instructions and data more efficiently within the cache. Now, notice that the caches, the level 1 cache and level 1 data and instruction cache are very, very small. So every time you access and fetch an instruction, they're going to go up and fill the level 1 cache. And as soon as the level 1 cache is filled, then the next instruction being fetched from the memory is going to have to override some instruction or some data from the level 1 cache. So it's not really a free lunch here. Once you run out of cache space, you'd have to essentially overwrite a part of it every time you fetch instruction or data from the lower levels of cache. So there's a lot of research done in the development of accurate and efficient prediction algorithms and patterns for hit and miss in terms of calculating which one of the instruction or data from within instruction and data level 1 or level 2 or level 3 cache needs to be overwritten. So basically one way is to just do round robin and go and fill the cache from the beginning to the end. When you're done, you can go and refill it from the beginning to the end. The problem by this round robin simple refilling of the cache is that maybe the first operation in the cache may be accessed much more frequently than the last ones. So if you do round robin, you're going to, every time you're going to overwrite all the bytes in the cache completely independently of how frequently they're used. So more efficient cache processing algorithms basically look at which bytes in the cache are being run or accessed more frequently, and you try to keep those and not overwrite them, and then try to overwrite those bytes and locations in the cache that are not being used, or the instruction or data that are not being used frequently when you need to overwrite. So I'm not going to go into the details of the cache systems, but this is one of the mechanisms by which you can speed up the operations by utilizing one CPU, but rather splitting it into several cores and then creating faster and more high-speed and efficient memory units for each of the cores, and then for the CPU itself to be able to create efficient patterns of memory access for your device to be able to process and alleviate the problem of throughput, of essentially bandwidth operations between your DRAM and your CPU every time you need to execute an instruction. The computing revolution that we all know started a long time ago, actually, in the 50s, when the first microprocessors were popularized after their invention. The devices, by today's standards, are fairly slow, and our cell phone, smartphones, essentially the computers in our cell phones, are thousands of times much more powerful than what the early microprocessors in the 50s were capable of doing. However, the microprocessor invention basically created the technology that was utilized back then to create supercomputers. These were machines that were very, very powerful, but by their standards of the time, and they were owned by large academic institutions, corporations, or by the government. Each of those machines were essentially thousands of times faster than our general purpose computing machines or PCs nowadays. And they essentially cost a lot of money. Cray was one of the founders of modern supercomputers, and he created Cray 1, which was produced in 1976. It had many thousands of individual cables that required to be connected together, so they would basically be used to perform essentially the computing capabilities that Cray was capable of doing. The Cray 1 essentially was a very, very expensive machine. It was about $8 million and could achieve about 160 megaflops, which is millions of operations, floating point operations per second. The speed nowadays is teraflops. It's essentially a million times larger than the megaflops that Cray 1 was capable of handling. If you want to think about it, a single Fermi GPU today can theoretically reach peaks of exceeding 1 teraflops of performance. After Cray 1, Cray 2 was developed, which was a significant improvement over Cray 1. And it started utilizing the so-called shared memory architecture. And it basically split the memory of Cray 1 into multiple blocks. And these were connected to 1 or 2 or even 4 processors at the same time. Today's supercomputers and GPU basically call these things symmetrical-based multiprocessing. Jaguar supercomputer, which was #1 supercomputer on the top 500 list of supercomputers back in 2010, was one of the computers, the supercomputers that was created by the Cray systems. In the 80s, there was a corporation called Thinking Machines that came up with a very interesting design that was used in the connection machine. It was a relatively simple concept that led to the revolution in today's parallel processing and parallel computers. They used these devices essentially very, very simple parts, very simple processing units, and combine them together to create a bigger processor that could theoretically perform better than the sum of its parts. They used 16-core CPUs, basically with the smaller processing units. They created the 16-core CPU, and then they installed about 4,100 of them in one machine. Instead of essentially creating a fast CPU, they combined a bunch of simpler CPUs, and then they combined them together to create even a better machine. This also led to the creation and utilization of the SIMD, the so-called single instruction multiple data, which is used in today's modern processors also, that essentially the first time they were using SSE, streaming SIMD extensions, MMX, multimedia extensions, or ABX, advanced vector extensions. The concept is to define a data range and then have the processor apply that operation over the data range. The connection machines basically created 64,000 processor cores, and each of those processor cores would be able to execute SMID instructions on its datasets. If you look at the Intel i7, we have 64-bit processors. Basically, that means that they can process up to 64 bits of data and instructions at the same time. Each 8 bits would essentially combine into 1 byte. Therefore, 64 bits will be 8 bytes of processing. The SSE SMID instruction set extends this 64-bit processing to 128-bit processing. With the SIMD instructions on each processor, you can eliminate redundant instruction memory fetches and generate 1/6 of the memory read and memory write cycles, compared to just fetching 1 byte at a time. Now, if you look at this SIMD, single instruction multiple data model, with the massively parallelized cores, 64,000 processors at the same time, you will see that you can achieve a lot of efficiency in calculating and processing the instructions and data. However, there's a catch here, and that is, with this massive multiplication, or rather parallelization of data in the SIMD model, you will end up with the need for a very good synchronization mechanism and very good communication patterns between the processors, so that you would eliminate redundancy of processes, as well as utilizing the essentially patterns of memory accesses. And we will see this with our CUDA programming and very interesting advanced concepts of efficient acceleration will essentially cover the approaches to try to eliminate the disadvantage of SIMD and the parallelization in this nature. Another interesting development in supercomputer was from the IBM's invention of the cell processor. And here you will see the hierarchical graph of a cell processor and how it was interconnected and created. The idea was to have a regular processor act as a supervisory processor, and then connect to it a number of high-speed streaming processors, or SPEs here. The regular PowerPC, or the core of this processing unit in the cell, acts as the interface between the streaming processors and the outside world. The streaming SIMD processors, or SPEs, as the IBM called them, would process datasets that were managed by your regular processor. So basically, you would not utilize your regular processor as a backbone processing unit, but rather as a distributing factor and a mechanism that would synchronize and make the cooperation between all those streaming processors efficient. This is a particularly interesting processor because NVIDIA used this technique in G80 and their subsequent GPUs. And now the CUDA capable graphic cards that NVIDIA puts out on the market, they're basically built off of this model, which is basically utilizing a massive amount of streaming multiprocessors and then coordinating them and organizing them in such a way that you can carry out your parallel processing. As you increase requirements, either the CPU, memory, or storage spaces that you need for a single machine, the cost will increase. So the problem is, if you wanted to utilize one machine with one CPU, even if you have a bunch of multi-core CPUs or processing units inside of it, the more you attempt to increase its processing power, say from 2.6 gigahertz to 3.4 gigahertz, you would notice that there's going to be a significant amount of increase in the cost associated with creating, utilizing, and operating that machine. Although the speed at which um, you will be able to perform is not going to be drastically much more than the speed of the smaller processing units. We'll see this in a little bit later, that we have reached actually that theoretical limit of increasing the speed of a single CPU, even multiple cores within the same CPU. This brings us to the problem of having very little return in the investment in terms of speeding up and powering up one single machine. This, in the 1990s, started a popular computing paradigm of cluster computing or multi-node computing. So the idea was, instead of speeding up and increasing the power of one single machine to its limit, what we can do is to create a network of simpler computers and then have them coordinate with each other and break down the processing units. So basically, you would create a network backbone. So you would have your network storage and your network switches, and then you would have each locality of your computing units interface with this network through a network interface. Each of those will have their own dynamic RAM and local storage with their own processor nodes, which could be any kind of processing unit. They could run Windows-based operating systems and Intel hardware, AMD and Linux computing platform, and so forth. And all that needed to be done is to coordinate and organize these within a cluster of computing machines that will be able to handle splitting up a process into smaller chunks that's manageable within each of those processor nodes, and then share data and instructions with each other through the cluster. Cluster of PCs typically run at the very minimum on a variation of Linux, and each node fetches its booting instructions and operating system from a central master node. There's one problem with cluster computing, and it's only as fast as the amount of internode communications that is necessary for the problem. If you have 32 nodes and the problem breaks down into 32 nice chunks, there's absolutely little requirement for internode communication. And so these can be parallelized and efficiently run on a 32 node computing cluster. However, the problem is that if this were not to be the case, if you have a 32 computing cluster, but your problem is not breakable into these clear-cut chunks, then there is a need for inter-network communication between your cores or between your processing nodes, and that is what basically brings your cluster down to a very low speed. As I mentioned, to address the problem of low bandwidth access and low throughput in terms of memory access, caches were developed and created to be able to use redundant data accesses and memory accesses and reuse them faster and efficiently. This can be also replicated and implemented in multi-node computing or cluster computing, so each of those local storages could actually act as an intermediate cache from the network. So each of those clusters can actually have a smart algorithm associated with them that would reuse the data as much as possible locally. One of the things that's very, very similar with the cluster computing and the GPU architecture is that they're fairly straightforward and fairly similar in nature. What we do have in graphics computers and graphics processing units, at least the NVIDIA CUDA capable units, is that you have a number of streaming multiprocessors. They're basically like CPU cores. So if you look at how the GPUs basically compute and how the architecture is spread out, you can see a good deal of similarity between the cluster computing and the cell processor that we talked about earlier, developed by the IBM. You've got your host memory, which is basically from your CPU, and it interfaces with each of the GPUs through a PCIe connection. The PCIe in turn connects to the graphics memory or the video RAM on board on your graphics card. And then you've got two levels of cache, a shared global cache between the streaming multiprocessors or the cores of your graphics processing unit, and then the onboard L1 caches within each of those streaming multiprocessors. So as you notice here, each of those GPUs basically that you see on the right here as a block diagram can be split down into its component blocks, basically a bunch of streaming multiprocessors that are connected through a cache to your video RAM and through your PCIe switch to your host DRAM or your CPU on the motherboard. So this is basically the model that we will be utilizing and working with, and the NVIDIA graphics cards that we work with in this class all follow the same pattern of hardware architecture. And we'll get to it, some details of this hardware as far as the implementation and the interconnection a little bit later in the class. But generally speaking, our GPU is composed of a bunch of streaming multiprocessors, and that is at the core of this ability for us to be able to parallelize our programs. So the more we can reform our algorithms into this format in terms of both instructions and data patterns, the better and the more efficiency we can get out of our computing with GPUs. Alright, now that we talked about the basic hardware architecture behind graphics processing units, let's take a look at what graphics processing units on modern CPUs actually represent. The GPUs, or graphics processing units, are basically there in almost any kind of PC that you get. They either come as a onboard chipset with your motherboard that are already integrated, or they would be added to your system alternatively through the PCIe Express or PCI Express connections. They provide a number of basic operations to your CPU, such as rendering an image in memory and then displaying that image on your screen. The GPU typically processes a set of complex vertices that create a bunch of polygons and then map them onto your fragmented screen, which is basically pixels that you will see on your monitors. After that, they apply a texture and calculate and interpolate the different amount of red, green, and blue color values that is going to be applied to each pixel, and then essentially rasterize or show the pictures on your screen. Sometimes, especially with the advanced shading mechanisms, your graphics processing unit takes care of calculating the shading of each fragment on the screen by means of processes such as ray tracing or other rendering mechanisms, alternative to the rasterization. When you take a look at NVIDIA's series, as early as NVIDIA 5000 series cards, you would see photorealistic examples of graphics rendering that were meant to be showing the massive power of graphics cards and what can be achieved by utilizing the specialization in terms of processing of your graphics processing units. To this end, graphics cards essentially have highly dedicated hardware that is just meant to perform these graphics processing units, from programmable shaders to texture memory and alternative kinds of onboard memory that makes a lot of these processes that are essentially as a core of your graphics processing quite efficient and quite fast if done and performed on your hardware on the GPU side. I'll show you two examples of what can be done and what has been done with the graphics cards. We'll start with the very early example that was done in 2003, and then we'll look at one of the latest examples that can be achieved over the NVIDIA series, GeForce series graphics cards. So the first example is this bubble demo. And by the way, you can go on the NVIDIA's website and download these demos and see what has been done. So this is a very early version of what can be achieved with graphics in real time. As you see here, this is a bubble, a highly reflective bubble, and I can move around and basically see the reflection of the world around me in this reflective bubble in front of me. And if you click on it, it's interactive. It'll basically nudge the bubble. And so all the processes, all the calculations of lighting and shading is done in real time. What is really impressive about this is that prior to the advent of graphics processing units and the so-called programmable shaders, you would not be able to perform this highly interactive shading program or shading algorithm in real time in application, because the shading pipeline or the pipeline of your graphics rendering would have been fixed. Now with the programmable shaders, what happened is that for each vertex, each three-dimensional point in the scene that you see here, you can actually write the equation of the light rendering, rather bidirectional light rendering equation, in program. And then and these are essentially very simple code snippets that are very, very C-like or assembly-like, depending on which shading language you choose. Then you will be able to program these. At this point, what happens is that the graphics calculation can be split into three parts. The first, or the front end of the pipeline, is your geometric calculation. Each three-dimensional points in the world will get transformed in terms of its rotation, its translation, and its scale with respect to the eye or the viewer coordinate system. Then those points that are renderable, or rather visible by the viewer, such as the points on the surface of this circle or reflective sphere, will be calculated and passed as fragments into my vertex shader and then into my fragment shader. The two shaders, vertex and fragment shaders, will take care of two things. One is to calculate the amount of light that approaches and hits the vertex in the scene and then reflects to the eye of the viewer to be seen, and two, the interaction between the light and the material on the surface of that vertex. And then from that point, it will be split into two processes: the calculation of shading for vertex, and the calculation of shadings for the fragment, that is essentially pixels that are rendered on the screen. So all that graphics talk, basically what happens is that it basically, for each of the pixels in this image that I see, it assigns a color to it. Now the reflection is a program that has been created into this shading mechanism. So if I'm looking at this pixel at the center of my screen, where my mouse pointer is pointing to, its color is being calculated in real time from the lights and the materials that are surrounding it. And so that's what the color I see on the screen. And that's the shading that is being applied. Another example that I want to show you is the example of a recent calculation of the graphics processing that is put out as a demo by NVIDIA GeForce. And I'm hoping that you can see this demo. It is highly realistic, rendered in real time by my graphics card, by the hardware. So what you saw in the previous two examples or demos were perfect examples of programmable shading or programmable shaders. And of course, on my NVIDIA graphics cards, that were really truly showing the power of um, uh, uh, applying, or rather utilizing, your highly sophisticated and specialized processings uh, of your graphics cards. Now, the only caveat here is that not all general purpose programs, not all general purpose algorithms are cut and meant, at least directly, in a direct fashion, to be efficiently used on GPUs, or rather to be integrated and incorporated into running on your GPU and efficiently and optimally utilize all of your graphics processing units capabilities. The most probably largest impediment in creating and accelerating rather an application is to make it into a instruction and data format, data pattern that is integratable within your graphics processing units. And we'll see this in this semester, and we'll see how you can rethink examples, algorithms, and programs in making them GPU operable. A lot of computing that's efficient for being run on a graphics card is, or has to be, in a format, or should be at least in a format, that makes use of the rendering pipeline, makes use of your graphics calculation pipeline. And what that is essentially the pipeline in graphics cards, the calculation of the pipeline in graphics cards is very good in terms of taking geometric data in the form of three-dimensional vectors of points or vertices, and then calculating successive geometric transformations on them. So if you want to think about, for example, when I was moving around, when the camera was moving around in the scene, in the Dawn demo, the second demo that we just saw earlier, each of the vertices that were a part of the scene, they would have a geometric transformation in terms of their rotation and their translation with respect to the camera, which it would be the viewer's eye, would be what is going to be rendered in the screen. So as camera moves, every movement, rotation, and translation of the camera will be manifested, will be translated into the rotations and movements of all the vertices in the scene. And all the vertices would be processed one at a time. And the graphics pipeline is very, very efficient in performing these calculations. So if you have a process, if you have a general purpose computing algorithm that can be reformatted and rewritten into or rethought as a part of successive geometric calculations, geometric transformations on multidimensional data, then you will be able to efficiently accelerate that and import that into your graphics card and utilize your graphics card. Unfortunately, as I said, not all programs are easily seen in that way, or can be even reformatted or reconfigured in that way. So it's generally speaking a very hard, or used to be a very hard thing to do as far as the calculations were concerned. Recently, NVIDIA has changed this shift. NVIDIA has changed this barrier and has made it possible with this new computing platform, new parallel processing platform, which is now termed CUDA, as an architecture that brings general purpose computing to graphics processing, or rather brings graphics processing to the level of general purpose computing. Still, to be able to fully utilize the CUDA's power, you would have to rethink some of the algorithms and some of the applications. But now, with the advent of CUDA, it is much, much easier to write in parallel than it used to be on graphics cards. Now with that, let's take a look at, or again revisit, our thoughts on single core solutions, or even single CPU solutions. See what the problem is with them, and what is the solution to go forward from that point on. The problem is, and I will talk about it in a future class, is that CPUs have reached the limit of their speed. We can make the CPUs faster. There's no doubt about that. And we have the technology to essentially double the size and the number of transistors that we can pack on a single chip, as predicted by Moore's law. The problem is power consumption. The power limits basically keep us at this point in time from speeding up the processors beyond a point. And as you have noticed in the past few years, the speed of the processor have stopped at about 4 gigahertz or so. So we won't see any doubling of the speeds anytime soon because of the primarily power limitations that is at the core of running faster CPUs. So the solution to that, as I mentioned, was the multi-core processing units. Essentially, instead of doubling up the amount of processors on a CPU and doubling its speed, what we will do is that we'll make 2 CPUs, 2 cores in the same chip, thereby doubling their speed. We have seen dual core, quad core, hex core, and so forth, and very soon we will see 16 and even 32 core CPUs that Intel and AMD are going to be releasing very soon. So with this, we are not actually speeding up one processor, but rather making multiple processors at the same size that we used to, and hopefully making these processors cooperate with each other side by side. We can speed up our applications as opposed to speeding up our hardware. However, there's a problem with this, and it has been over the past few years, and that is that although we may have a quad-core CPU on our machine, when we write a program in serial, we won't be able to essentially utilize the quad core, or rather 4 or 8 cores of the processing units at our disposal efficiently to make our program run 8 times faster. If we write a program in serial, it's going to essentially utilize one of the cores, thereby having the same speed as if we were writing our program with a single core CPU. Now that requires a little bit of thought, a little bit of rethinking of your problem, and a little bit of computing platform um, cooperation between the hardware, that is your CPU, multi-core CPU, and the software, that is your program, as well as your operating system on which your program is running. So at this point in time, we are at the point that there is a good deal of capabilities out there that you can use, and a good deal of interest, but it hasn't reached that critical mass that everybody goes to the point that, at this point we will essentially stop thinking about serialized programs and start writing programs, or rather multi-core programs. So in many software engineering companies and the industry, if you write a program, a serialized program that runs relatively nice with a single core, or rather even a quad core, there's not much interest in making your program essentially utilizing the 4 cores of your CPU. There may be several reasons for that. One is, if you write a program that runs really fast, what is the difference between just running it fast or 4 times faster than it is, especially asymptotically when you're dealing with a lot of data? Because a big O of n and a big O of 4 times n are essentially both in the order of same order of magnitude. But things may be changing and trends may be shifting towards support of multi-core calculations and multi-core programming in the CPU market. However, things are slightly different in the GPU market, and that is quite visible with the look at the CPU performance and the GPU performance. If you look at the relative computational powers of GPUs and CPUs, we get a very, very interesting look. We start to see a divergence between the computational power of CPUs versus those of the GPUs, starting at about 2009. The computational power of the CPUs over time have been steadily increasing, kind of sort of doubling every other year or so, but it's been changing in a linear fashion. So you may have we had like single core CPUs in 2006 with so much power, and in 2012 the difference or the performance increase within the CPUs are still within the same order of magnitude. It's only 1 order of magnitude larger. When you look at the performance power, or the gigaflops, rather 10 floating point operations per second of a GPU, you would see that the GPU performance is actually increasing in more of an exponential term compared to those performance measures of CPUs. There are a couple of reasons behind this. One is that since GPUs are specialized hardware, you can essentially make them more efficient and run more efficient for that specialized calculation that you have in mind compared to the CPUs. Remember, with the CPU, it's a general purpose computing tool. It is designed to run general purpose applications, which means that its processing power, since it has to be generalized, it would be much more limited. However, it is going to be powerful, but much more limited in terms of the flexibility of the architecture. Whereas for the GPU, since you already have specialized processing or computing capabilities in mind, you can optimize that computing capabilities. You can optimize your hardware to support that computing capability. The second reason for this divergence in performance is that with CPUs you can create quad or 8 or 16 or 32 cores. With the GPUs, with that same amount of power consumption, you can actually increase the number of cores rather drastically from one generation to another. And these two factors together would essentially amount to a huge improvement in terms of number of floating point operations that a GPU can support compared to those that a CPU can support. Now combine that with a programmable platform, a programming paradigm that brings that multi-threading on a GPU level, on a GPU side, to the programmer, to the application programmer, such as what CUDA does, then you will be able to see a very clear pathway towards developing parallelized algorithms and parallelized programs that could utilize general purpose, or rather special purpose architecture of a GPU and apply general purpose algorithms, general purpose computing programs onto the specialized hardware architecture of a graphics processing units. And that is what we will be doing with our class here. And what we'll see is how you can essentially understand the architecture of CUDA, both on the hardware side and what it does allow us to do, and also in the software side, what we can do and what we should not be doing to be able to efficiently optimize our programs for being ported onto a device, or rather our graphics card. There are alternatives to CUDA, and with this class we're going to essentially focus on NVIDIA range graphics cards and the CUDA capabilities. But if your GPU manufacturer is ATI or AMD nowadays, you can basically utilize their platforms in order to be able to write programs. There are I'm listing a couple of alternatives to CUDA here. The OpenCL and Direct Compute, which we'll not be discussing and working in this class, are also out there. The OpenCL is an open royalty-free standard supported by NVIDIA, AMD, and other graphics cards. And you can basically take your GPU and CPU and write your parallel programs utilizing this API. It works both for Windows and Linux, I believe. Also, Direct Compute is a Microsoft alternative to CUDA and OpenCL. It's essentially created by Microsoft operating system, and it also utilizes DirectX 11 API as its application programming interface, and it allows you to write your programs onto your graphics card. Basically, if you're very familiar with C++ standard template libraries, they will be also putting out a standard template-like library for the Direct Compute. There are also alternative CPU tools out there that you can use. The main processing languages extensions that are out there are MPI, OpenMP, pthreads that are developed for Linux. And also for Windows, there is the Windows threading model and the OpenMP that you can use, and essentially to be able to write parallelized programs to utilize multi-core and multi-threaded applications for accelerating a generic application and a generic algorithm. So this should give us a very good overview of what we will be seeing in the class, and a good history of what has been developed over the past several decades, and has reached to the point that we as application programmers and software engineers will be able to tap into and write programs that are highly efficient in terms of utilizing every bit, or rather every piece of hardware at our disposal to run our programs highly efficiently. With this, I will close out this our introductory unit, and what we have covered so far is the fact that where and how you can download and install our programming tools for this class, namely the CUDA software development kit and the OpenCV computer vision libraries. We wrote a very simple program that made sure that both our libraries work and that our CUDA computing platform is installed properly for us to write our programs. We saw a history of parallel processing from basic serialized architecture to supercomputing applications and hardware, and to how graphics processing units modeled supercomputing architecture in hardware, and then how CUDA and other alternative programming APIs and software development kits have brought the massive computing capabilities of our hardware and graphic processing units to a general purpose computer programmer such as us. And then in the next unit, we will be looking at some hardware related overview of CUDA and how it is integrated within your system. And then from that point, we will start looking at both hardware as well as software and data patterns that we can use for parallel processing in our applications. Thank you very much for listening to these lectures, and I'll look forward to talking to you in the next unit.